Okay, here we go with double displacement reactions and solubility. Now, you already know what a double displacement reaction is, but we're going to take a quick little review and then we'll get into the solubility side. Double displacement reactions. With a double displacement reaction, of course, you have two normally ionic compounds, which we're calling A and B, but they're always going to be the positive ion and the negative ion, the positive ion and the negative ion, and two of them switch places. Now, you can think of it as the two positive things rotating out, or you can think of it as the two negative ions rotating out. It doesn't really matter, but we end up with A and D. And a couple quick little things about that you don't need to write down because you already know this, is that the first element is still the first element. So when you get to the point where you are trying to predict the products, you're not going to end up doing the B of the first one with the D of the second one, because those will be two negative ions going together, and that's not going to happen. Second thing is that the charges on the metals do not change. Now, of course, with this very generic example, there are no charges. So let's take a quick look at an actual example. Working through this one, you can say, well, chlorine is a -1, there's two of them. That means this copper is a +2, and sulfur is a -2, there's three of them, so that makes this iron a +3. And if you look at the product side, this copper is still a +2 and this iron is still a +3. So the charges do not change. That's really kind of important in a double displacement reaction for predicting the products. However, not really all that important for what we're talking about right now. So we're going to take a quick little side trip and then come back to double displacement reactions and solubility, because solubility is not something we've talked about quite as much. So we know that ionic compounds are solids at room temperature. That all by itself, you don't really need to write it down. I'm sorry if you've already gotten it started, but ionic compounds are solids at room temperature. And that's one of those typical properties of them that we come across. And they are typically soluble in water. When I think about salt, dissolves into water. A lot of ionic compounds dissolve into water, but it's possible that they can have a very low solubility. Now, a little side note to their side trip. To say something has a low solubility is not the same thing as having no solubility, but for us in this section, we're going to end up treating it almost the same thing. If something has a low solubility, it's actually going to be very, very low solubility, to the point that we would say, yeah, it really didn't dissolve at all. And if you have something that has low solubility, then it doesn't matter where it comes from or how you get it, it will have the same low solubility. So if I start out with a compound and I add it to water, or if I produce that compound. Okay, so this is how we're going to get back to our double displacement reactions. All right. If you have your textbook on page 137 and actually two other places, there's a solubility table. If you don't, it's okay. I'm going to show you a slightly smaller version. It's going to be set up exactly the same way. And we'll be bouncing back and forth with this table a lot, so you don't have to worry about writing it down. You will have the table or access to the table, or I'll give you another version of it anytime you need to do this stuff on a test, on a quiz, or what have you. So you don't ever need to write this table down. The table I'm going to show you is organized the same way, but is a little bit smaller than the one in your textbook, but it won't matter for this. So the table, the one in the textbook is going to be like this, a little bit bigger, maybe prettier too, but it's going to be organized the same, and that's going to be key. The table is always going to be organized by the anion, the negative ion. So it'll be sectioned off according to ions, the anions rather, and certain ones that kind of group together. So the patterns in solubility here for chlorides, bromides, and iodides are all the same, so we group them together. The pattern in solubility for these two down here at the end, well, second from the end, they're all the same, so we can group them together. Now the one in your textbook has a few columns that I don't, but that's okay, because again, it doesn't matter for this, and when you need those other columns, you will have access to them. What about the cations? What about the positive ions, all those metals? Well, that comes in on the side. And you'll notice that this is where we start to see the differentiation, the patterns showing up. So we'll have one row that's high solubility, and these things dissolve. So high solubility means you get dissolving. You don't need to write this down because it'll make sense later, which means you'll make a solution. And the low solubility, well, you don't. It doesn't dissolve well, and it doesn't make a solution. Now you might be wondering, well, what about those ones right on the borderline? The good news is there really aren't any. Things that have high solubility dissolve quite well, quite noticeably, and things with low solubility really, really don't. Your textbook actually has numbers, and we're not ready for the numbers yet, but basically it's a zero point 0.1. Anything 0.1 and above is high, and zero point 0.1, well, actually below zero point 0.1 is low. Well, what about the ones that are zero point 0.1? Again, there really aren't any. So low is usually very low. Okay, let's fill it in. Most ions, most metals with chloride, bromide, or iodide form high solubility compounds. These are the exceptions. Now again, the one in the textbook has a couple of other ones, doesn't matter for us, and in most cases won't matter for us at all, but certainly not for today. Whereas this one, the OH, right beside it, most of them form low solubility compounds, and there's a few exceptions. Okay, so let's try a few and see if we can make this table make some sense. So one kind of question that you're going to see is this: determine the solubility of, and I'll give you a chemical formula. It'll be an ionic compound, and I'll ask you to figure out if it's going to be high solubility or low solubility. So what do? You go to the table. We're looking for, this was iron 3 chloride. So we start by looking at our chloride. And okay, here's chloride right here. Most of them are high solubility. These are the exceptions. Now I did say that there were a few that should be on this list that I've not included, but iron is not one of them. So I don't see iron listed in low solubility, which means iron must be one of the high solubility ones. So I come back and say that iron 3 chloride has high solubility. Easy. Take another one. CuOH taken twice. We might not have the nomenclature for this yet, and that's okay, but I'm going to be looking for this in the table, and then secondly looking for the copper. Back to the table. Here we go. So here's my OH, and I have this list here, group 1, well that's lithium, sodium, potassium, and so on, NH4, Sr2, strontium, and barium. I don't see copper in the top list, so it must be in the bottom list. And that corresponds to low solubility. So I would go back and say that this compound has low solubility. We'll do one more. PbSO4 taken twice. Now this is a bit of a trickier one, and it shouldn't be, but it sometimes will be. So I'm actually going to write this formula down when we look at the table in a moment. Okay. So we had Pb bracket SO4 bracket 2. Now why does it matter, and why is this one tricky? This ion, SO4, has a 2- charge. There are 2 of them, which means I have a total charge of -4, which means I have a total positive charge of +4. That becomes important. All right, so here's my SO4. Most have high solubility except this list. Well, here's Pb plus 2, but I'm looking for Pb plus 4. Now, it's possible that Pb plus 4 could be in this list and it wasn't written down. That's possible. But based on the information that I have right now, I don't see Pb plus 4. I don't see lead plus 4 in the bottom list. So I'm going to assume it's in the top list. And that corresponds to high solubility. Now, am I going to be absolutely correct all the time? Maybe not. But outside of making those exceptions, outside of saying, well, maybe it should have been in this list and it wasn't, that's how I would use the table to predict the solubility of this compound, and because it's lead plus 4. All right, so that was a bit of a side trip using the table and understanding solubility. Let's get back to those double displacement reactions. We know how to predict products of reactions. We know that this is going to be a double displacement reaction. We know that this is a positive negative thing, and we know that this beside it is a positive negative thing. So we're set up perfectly for a double displacement reaction. We know that the 2 metals are going to trade places, and we know that the charges are going to be the same. Now, looking at it, this is a -1, that's a +1, although I knew this was going to be a +1 because sodium is always +1. Find that one somewhere in the table, that's a -1 each. There are 3 of them, so I have a -3. That means iron is +3. So my products, I'm going to have to keep those things together, and hopefully you were doing them while I was talking, and I end up with these products. This reaction is not balanced. If you want to balance it, I would need to have a 3 in front of my first reactant and a 3 in front of my last product. but for what we're doing, it doesn't actually need to be balanced. So I'm going to take those numbers out, and hopefully I don't confuse anybody, but I want to keep things nice and simple. So our products were, need the table, this one, and this one, I think. Let me just double check. Yep. So I'm going to start with the OH. Here's OH. Group 1 is okay. NH4, strontium, barium. Oh, iron must be in this list. So I'm going to say this one is low. NO3, here it is. Oh, this is nice. All compounds of NO3 are soluble. I don't even have to keep any look anywhere. So this is going to be high. So what I'm going to have is I'm going to have a mixture of a low solubility and a high solubility. Well, what's going to happen? What's going to happen is I'll get a product that is a solid. I get a product that does not dissolve. Okay, so an ionic compound is solid at room temperature unless it dissolves. If it doesn't dissolve, it's still a solid. Well, if I have a solid inside a liquid mixture, it's going to look like a powder, and we call that a precipitate. So if you've been writing stuff down or you haven't been writing stuff down, this is worthwhile. A solid product is called a precipitate. It's got to be a product. That's a key word, and precipitate is a key word. Because I'm just going to use that. I'm going to say find the precipitate, or identify which one is going to be a precipitate. And the whole mixture is going to be cloudy. So if I've got a mixture of two things and one salt dissolves well, but the other one doesn't, the whole thing is going to look cloudy. And if I have it so that one dissolves well, high solubility, and one doesn't, all I need to have is that one that doesn't, and it's going to affect the whole thing. So I've got a picture here, and I want you to kind of ignore the most obvious thing for a moment. On this picture, I've got this. So that's one of the reactants being poured in, and if you look at it, if you didn't otherwise know, it kind of looks like water. It's clear, has no color. And I want you to look down here as well, whoops, a little bit further over, not the yellow, but inside the beaker where the mixture hasn't happened, where the reaction hasn't happened, it again looks like water. So I have a clear colorless liquid being mixed with a clear colorless liquid, and what I get is, oops, not there at all, a precipitate. That's what I'm talking about. It doesn't have to be, and it actually won't be, that both products don't dissolve, that both products have low solubility. It's usually going to be one has low solubility. So here's the kind of question where we're talking about double displacement reactions and solubility. I'm going to get you to write these down, and what you're going to be doing is you're going to be looking at the products. Don't worry about the reactants, because I'll tell you two things about it. Number one, all of these reactants are soluble, and we would usually put the little bracket behind there with an AQ. I just didn't put that in here. So AQ for aqueous, dissolved into water. And somewhere along the line, we're going to have a product with an S, solid, whether it's the first one or the second one. That's what you have to figure out. Second thing is, if we're talking about a precipitate is the solid product. So I only need to look at the product side of the reaction. All right, in a moment, I'm going to flip forward into the solubility table, and that's where I'm going to leave you. If you have your textbook, by all means use the one in the textbook, but if you don't, the table that you have here, simplified or shortened as it is, will still be able to do all of the reactions. If you have a reaction where both of them have high solubility, then you can just write no precipitate, no PPTE, short form for precipitate, and that'll mean that you've checked, you've confirmed, nope, both of those things dissolve well, there is no precipitate, no solid, and then we can go from there. So coming up, here's the table. Okay, so you may need to pause this and have it there when you're working with the reactions. Okay, one last thing. It doesn't really fit with the bumper sticker well. Another one of those lame science jokes, but I got a laugh track this time, so it makes it funnier. If you're not part of the solution, you're part of the precipitate. But see you in class. Talk to you later.